So we are overjoyed tonight to have as our guest Dr. Eric Smith, who is from NASA headquarters. And so, Eric, why don't you please come and join us? Patrick. Yeah. So let me tell you two quick stories about Eric. One is we've known each other for years because I was on Hubble, he was on Hubble. We're Hubble cousins, Hubble siblings together. And then the other thing is he was supposed to come here last January and do this talk, but we had that pesky little government shutdown. So some of you might remember that we had to say, well, Eric Smith had to, they didn't let him travel. So just a mere 9 months later, we are so glad to finally welcome you here. And so, Eric, why don't you tell us a little bit about Webb, and then we'll have a chance to ask questions and discuss.
Okay, well, thanks, Laura. And I guess the delay worked out well because now we have some really exciting news to talk about here. One of the first things that I like to talk about when I talk about the James Webb Space Telescope is say, well, who the heck is James Webb? So this is the James Webb that we're talking about here, not the ex-senator from Virginia, but the man who was really the architect of the Apollo program, NASA's second administrator. But the reason it's important for us here as scientists is that he is the person that insisted science be done within NASA. Many of you may remember that the Apollo program was really showing American superiority to the Soviet Union. We're going to beat them to the moon. We have the best rockets, all that. That's really all that Kennedy cared about. But Webb, who was a bureaucrat by training, knew how to work the levers of government, knew that he had to have the best scientists and engineers to complete what the president wanted. And to get those people, he had to let them do their science and engineering research. So the only reason we have science at NASA is because of James Webb, who was a lawyer by training, actually. So why are we building the Webb Space Telescope? Well, we're building it because of something that Hubble couldn't do. After Hubble was repaired in 1993, the director of the Space Telescope Science Institute, Bob Williams at the time, said he was going to do an experiment and point the Hubble at a blank piece of sky. I think there were maybe 4 stars in the field of view, otherwise completely blank, to see what could you see if you really exposed for a long time in the sky there. And of course that picture now is famous as the Hubble Deep Field. Then there was other instantiations of it, the Hubble Ultra Deep Field.
The Hubble Super Duper.
The Super Duper, Supercalifragilistic Deep Field. What they were looking for in these deep fields were signatures of the first stars and galaxies. Can we see the universe turn the lights on, in other words? And what they found was no matter which one of these objects they looked at, it was not one of the first galaxies. And so as capable and as amazing as Hubble is, there are some places where it has fallen short. So that actually told us, now this is in the mid-90s, that what we needed to do if we wanted to see some of these very first galaxies was to build a larger telescope and one that was optimized for the infrared. And I'll do a brief little physics discussion about why that's the case. So galaxies emit a lot of their energy as starlight, which we can see in the optical. And so here you see the black body spectrum, the amount of energy that comes out as a function of wavelength, peaking at around the optical part of the spectrum for a redshift of 0 object. So redshift 0 means it's local in our own universe. Now, as you're looking out in space, you begin to look back in time. Astronomers measure that in terms of redshift. And if you march out in time, farther back in space, the wavelengths of the light get stretched by the expanding fabric of space-time. Think of if you were shaking a rope with a friend of yours and you started backing up with it, you would be flattening out, increasing the wavelength. The same thing is happening as light travels across space-time to us. It's getting shifted to the red. And so if you move to a redshift of 3, you can see where that peak used to be in the optical. It's now in the infrared part of the spectrum. And if you go out to a redshift of 10, which is about where Hubble can see to, maybe a little farther than that now, you're starting to get into the mid-infrared. So to find these early galaxies, you would like to optimize to be an infrared telescope. That's where the light is. The other thing that redshift does is it decreases the surface brightness. It makes the objects harder to see. They've become fainter. So you need an infrared optimized, bigger telescope. And that's really the genesis for the James Webb Space Telescope. It was this phenomenon that Hubble looked for, couldn't quite make it, and it told astronomers, the astronomical community, what the next step needed to be. Now, one of the benefits you get of having an infrared telescope that you've built for this is that it's also going to be very capable of looking at objects at cooler temperatures. Again, if you look at starlight, stars emitting a lot of their radiation in this visible part of the spectrum, that's a characteristic temperature, several thousand degrees Kelvin. If you have an infrared optimized telescope, it's going to be more sensitive to cooler objects, and so you'll see the universe in a slightly different way. You'll be looking at different physics, and we'll be most sensitive to objects in the hundreds of Kelvin range locally. This is more for experiments we would do within our own galaxy. So these are the basics of the physics behind Webb. Now, what were some of the things that astronomers were thinking about when they said, hey, let's build this large infrared optimized telescope? Well, you might imagine they had plenty of things they wanted to do. So initially, it was this emphasis on finding the first stars and galaxies. But since you can see those first objects, you can now watch them evolve throughout cosmic time. So you can do a lot of experiments, as it were, about the structure and how it builds up in the universe. You can begin to penetrate, because infrared radiation penetrates gas and dust clouds more effectively than optical light. So you can watch stars forming in dust clouds within our own galaxy. The second to last question up there was something that we didn't think about when we were first conceiving Webb, because in the early 90s, does anybody know what the exoplanet count was in the early 90s? Well, it was, when we were started at Webb, there was 2. We knew about 2 around a pulsar. There was no way you could observe them with Webb. But it really wasn't part of the initial thinking. Now, when we talk about the instruments, you'll see that we actually will be super capable, but it wasn't really by design. It was only because of the incredible power of some of the instruments. So just for comparison here, people may be more familiar with Hubble. This is just a little statistics comparison between the two. So Hubble's mirror is about 2.5 meters in diameter. Webb is 6.5 meters in diameter, so more collecting area. Hubble is pretty beefy as far as telescopes go. It got to ride up on the shuttle, so they didn't really have to worry about mass, saving mass that much. We had to worry about that a lot. We were just a bigger observatory, so even though we are a larger collecting area, we're about half the mass of Hubble. Our wavelength coverage is from the reddest parts of where your eye can see out to the mid-infrared, whereas Hubble can see a little bit into the infrared out to the ultraviolet, so different wavelengths optimization. Hubble's a room temperature telescope because it's in low Earth orbit. Because we're infrared optimized, we want to be cold because you don't want to see the signal coming from your telescope. So our telescope is very cold. And also, unlike Hubble, we will be far away. Hubble was accessible by the shuttle, got repaired. We're going to go 1 million miles away, 1.5 million kilometers away, and we'll talk more about that later. Let's see. Last point there, Hubble went up on the shuttle, and because we're a partnership with the European Space Agency, they are giving us a ride on their Ariane 5 rocket. So a little bit about the telescope here while this little animation runs. We talk about 3 big components of it. The telescope itself, the gold hexagonal structure everybody thinks of. The spacecraft element, which includes that sun shield and also houses the propellant and avionics and batteries and things like that. And then behind it, those white structures you see there are the science instruments, and we have 4 of them. In the order they're listed there, the mid-infrared instrument is the one that sees the longest wavelengths for us. It was built by a collaboration of European countries, and it has contributions from the Jet Propulsion Laboratory. They did the detectors and the cooling for it. The near-infrared spectrograph was given to us by the European Space Agency. The big U.S. instrument is the near-infrared camera that was built by Dr. Marcia Ricci at the University of Arizona, working with Lockheed Martin in Palo Alto. And then the last bit there, the fine guidance sensor and near-infrared imager and slitless spectrograph, is the Canadian Space Agency contribution. And so they have a functional part, the fine guidance sensor, which keeps us locked on targets. I like to say Canada is helping their unruly neighbor to the south stay focused in there. And then the near-infrared imager and slitless spectrograph is their science instrument. So we knew we needed cameras and spectrographs. We needed a big telescope that looks a little bit different. We could talk more about that later. But to realize those things, we had to make a bunch of inventions. We had to invent technologies that actually enabled it. I won't go through all of them here, but some of the most amazing ones I do have pictures of later on are the backplane, the superstructure behind the mirrors themselves, which are beryllium. We made them out of beryllium, mined in Utah, throw away 95% of the mass. So really all you have is a millimeter or two of beryllium sheet, whose only job is to carry 1,000 atoms thick of gold to do the infrared reflectivity. So all that structure is there to carry 1,000 atoms of gold to reflect the infrared light. So speaking of the science instruments, that's just these were the things in white in that animation. In the upper left corner is the near-infrared camera. This will be the workhorse camera that you'll see a lot of pictures from. It's actually a redundant instrument. It's got a top and a bottom half. They're identical. And that's because this is also the instrument we will use to make all those mirrors work like one. And so it's completely redundant. Should one camera fail, we could use the other one, and that way keep all the other instruments able to work, and you wouldn't lose their functionality. The upper right is the near-infrared spectrograph. That's the European Space Agency instrument. For scale, because there isn't a person in the picture there, that's about the size of a baby grand piano, that optical bench there. It has a micro shutter device inside it that was built at the Goddard Space Flight Center, and that's about 100,000 or so little shutters that are about the width of a human hair that you can open and close, so you can isolate particular objects on the sky and let their light into your spectrograph. It's the first time we'll fly something like that in space.
Wow.
Bottom.
That's incredible.
It is an amazing instrument, and I think it's the one that astronomers will, it'll really be a workhorse, but I know it's going to be one of those things, it's going to be more complicated than everyone thinks when they first heard it, like, oh yeah, I can do that, and then they start working on it. Oh well, it's going to take a little longer. The mid-infrared instrument, bottom left, it's both a camera and a spectrograph there. It's being assembled actually at the University of Edinburgh, was where they had been putting some of that together. And then the bottom right is right before it was shipped. That's the Canadian Fine Guidance Near-Infrared Imager and Slitless Spectrograph. So all four of those instruments got put, now looking at the left-hand side here, into this cage. We called it an integrated science instrument module, and that was lowered into the telescope structure, and on that picture you can see the goal of the telescope. It's pointing down at the floor. This is out at Goddard Space Flight Center in Greenbelt, Maryland, and then the picture on the right is just the very end of that process where they've lowered it into the ISOM compartment. Then once that was all together, we needed to test the telescope and the instruments together. So first a little bit about how that telescope works. We're called a three-mirror anastigmat design. So we have three main mirrors, elliptical, a hyperbolic, and another elliptical tertiary mirror. But there's also a flat steering mirror at the end that we can use so we don't have to slew the telescope for small motions. We can just move that mirror a little bit. The mirrors, as I may have mentioned, were made of beryllium. Each mirror segment can be controlled in piston, tip, and tilt, and we can also adjust its radius of curvature. So even though they look flat to the eye, there is some optical power in them, and you can sort of push the center in and out. We know that when we launch this, it will be out of focus. Just giving you that warning right now. But we can adjust it. In fact, because it's this infrared telescope that has to work at extremely cold temperatures, the mirrors now, they're out of focus because they're at room temperature, and it only comes into focus when it's extremely cold. It's part of the reason why it takes us so long from when we launch to when we get data back. We have to cool down so that the mirrors are smooth as they were supposed to be at cold and not bumpy as they are at room temperature. So did we test that? Well, of course we tested that. We took it down to the Johnson Space Center where we refurbished the old thermal vacuum chamber that the Apollo mission used to test the Apollo spacecraft. They used it to heat the spacecraft so they could test the effects of moving the spacecraft and how that might affect the astronauts. And of course we wanted to be just the opposite. We made it a cryo chamber so that we could drive things very cold. It's interesting when you go down there to work, on the side of the chamber, it's a National Historic Register facility. So I thought that was kind of cool that we're doing modern day technology in this historic structure. And they didn't make us wear skinny black ties and get through that. So that was good. We didn't have to go to all that trouble. But this was after we did the test. And sure enough, they were able to move all those mirrors and exercise all the instruments. And I'm delighted to say that it will meet the scientific promise it has once we get it on orbit. Everything worked as planned. So that was very exciting. The structure that lies behind that telescope, even though we're just carrying those 1,000 atoms of gold up there, 1,000 atoms thick of gold, it's this backplane, this structure made of a carbon composite material. It comes in thin sheets that they lay up and epoxy together. It's incredibly strong, it's very light, and it has the property of a lot of things on Webb. Its behavior as it changes temperature is very well calibrated. And you can see the little note up there about how precise it has to be. We have to know how this is going to change to a fraction of a human hair, because that will affect the image we get back on the telescope. In fact, we were able to see when we were testing it down at the Johnson Space Center, there was a camera at the top of that chamber. They would shine down, and that chamber wasn't as cold in the top as the rest of the chamber. And just that very slight exposure to a few degrees temperature caused some of the insulating material to feel a change in temperature. And that incredibly tiny stress could be seen through the backplane. So it carries that information to the optics, and we have to be able to correct that out, and they were able to. So the other characteristic thing, other than those gold hexagons, is the big sun shield for Webb. It's our parasol that we use to block infrared light. Most telescopes block the stray light with a tube. We are a naked telescope. We don't have a tube. That's because we have most of the sources of infrared light to one side of us. We'll see that in an animation later. But by keeping the sun, the earth, and the moon more or less on one side, we only need to protect ourselves on that one side from this, the infrared radiation. Being a fair-skinned person, I love that last little thing there, SPF of 1,000,000. I could use that. Now, the spacecraft element, which is both the sun shield, here we see it all folded up in its launch configuration, and then the spacecraft bus, which is essentially it's the infrastructure that enables the whole observatory to work. It's where we have our reaction wheels, our gyroscopes, our fuel tanks, the batteries, the electronics. They had completed their environmental testing, so we subjected them to the vibration of a launch of an Ariane 5, the sound from an Ariane 5, and the thermal stresses they will feel, which are different than the telescope. This part only sees more or less room temperature. It sees the sun all the time. The telescope never sees it. And it's in fact that great contrast in temperature that means we can never test the whole thing in a thermal vacuum chamber on Earth. There's no chamber big enough that would let you get the heat on one side and the cold on the other side and not be an infinitely large chamber. That's what we have space for. So, 2 weeks ago today, as Laura mentioned, it all came together finally. And if you were to take a trip just a couple miles south of LAX Airport at the Northrop Grumman Redondo Beach facility, if you know anybody who works there, make sure you get them to go to the observation room. Anybody can get in there. If they work at Northrop, their badge will let them into the observation deck, and you can go see it yourself down there.
Anyone from Northrop in the audience? You need. Oh, great. Well,
Yeah.
you've got 100 new friends.
I saw day before yesterday. It was a thrill, a treat.
It's wonderful. Well, okay, everybody, there you go. Now, before we talk a little bit about some of the science that we suspect they're going to do, I'll take time out for this is a paid commercial break here about the people who've made this all happen. So there's a lot of words up on the slide here, but this is an international endeavor. Large, great observatories, like Laura mentioned, are pretty much all built with international support these days. And so I think Spitzer may be the last such observatory that will ever be built just by one country. They're all future missions are all international partnerships. The lead for this was the Goddard Space Flight Center, but we had contributions from almost every other NASA center. ESA supplied us with an instrument and the ride, the Ariane 5, which is the world's most successful, reliable rocket of its class now. So that's very comforting to know. You have a nice, safe ride. Canada supplied that fine guidance sensor. Both ESA and Canada are supplying people to work at Space Telescope Science Institute. So there'll be scientists on staff there. And then the main industrial contractor was Northrop Grumman, and they worked with Ball Aerospace and many other companies to make this come together. And of course, like Hubble, this will be the science program will be run by the Space Telescope Science Institute, but they will also fly the bird, as they say, this one. So it will actually be operated from Baltimore, where STSCI is. Hubble was run out of Goddard. So speaking of where things were built, this is just a chart we show of all the companies across the U.S. that had some say or they contributed to Webb. And we like to take this around with us if we're traveling to any place in the country to try to mention if there's anybody nearby. Of course, here in Los Angeles, you have Northrop Grumman nearby, but there are other companies in the area. One last bit on the commercial. Some people like to talk about NASA spinoffs. I view that they're valuable. They're a side benefit. You don't do these things to get spinoffs. There would be cheaper ways to get them. But it is nice to know that these incredible mirrors we had to make and invent have allowed another company to use the metrology technology to make something that eye doctors can use now for improved LASIK measurements. We're using a lot of the other metrology techniques for higher tech business. In what I consider an amazing piece of future heritage, the application-specific circuits we had to invent were invented early enough in the program that they actually got to use one on the last servicing mission for Hubble. So we invented something and sort of gave it to our predecessor. That was pretty interesting. And then the detectors we had to build have become the foundation for missions after us and will be for future missions as well. So we're all together. We're down at Northrop. We have about 1 year of testing to go. They'll practice a deployment. We'll see that in a second. Then they'll fold everything back up, and then they'll take the whole observatory in that configuration you saw before, where it was folded up, and they'll, again, shake it like it's going to go on an Ariane. They'll blast it with the sound of an Ariane, and then they'll unfold it all again and fold it back up. So in about a year, it'll be ready for its launch, and that means we'll take a boat ride. We are going to take a ship from Los Angeles through the Panama Canal down to French Guiana, where it will be launched by the European Space Agency. It sounds counterintuitive, but that's actually how Arianespace, the primary contractor, get their large parts down there too. They barge them in, I like to say. That's an easier route. They're very close to the coast, and the rest of the country's infrastructure isn't as good for things like large bridges taking a lot of stress. So we will take a ride, a boat ride down there.
Take it to ride.
Sure.
Now, I mentioned that we're going to be 1.5 million kilometers away. Anytime you have two bodies that orbit one another, a two-body system will have 5 places that are stable or semi-stable in the gravity field of this rotating system. This was discovered by a French mathematician in the 19th century, LeGrande, and where we are going is that L2 point. And so it sits outside the Earth and the Sun. And if we run this little animation, what we actually do, you see the moon whipping around the Earth there, and you'll see Webb come in, and we actually orbit about that second Lagrange point. So we keep the sun shield, keeps the sun, the Earth, and the moon on one side of us. We're not in the shadow of the moon because we got to be able to communicate back to the Earth. But the size of the sun shield means that we can keep those things on the hot side and keep the cold side on the cold side. So now the part that gives everyone, causes their heart to skip a beat. This is how we get out there. This is an animation that folks at Northrop Grumman put together showing the sequence of events. Once we get released by the upper stage from the Ariane, we go through a series of maneuvers and deployments. You can see on the top the time after launch, the distance will come up with the activity, and you can see a little graph showing where we are in our journey. The solar array comes out very quickly, so we have power. We start to do any course corrections we need to make sure we're going to the right orbit out there at L2. The smaller the correction we have to make, the longer our life is because it saves fuel. Right about the time we get close to the moon, our high gain antenna comes out so we can communicate at a high data rate. You can see about 2 days we're past the moon. Now we begin the major deployments where what's called a pallet that holds the sun shield, the forward part folds down. We'll follow that by folding the back part down. I got to watch them test this at Northrop Grumman. They do a gravity offload to test the system. Now, once those are down, we want to move the telescope away from the spacecraft because it is a little warm itself. So we telescope up on a tower about 5 feet. Now, the covers that protected the sun shield during launch are released and they roll back. Some covers in near the spacecraft core do the same thing. And once those are released, we can actually begin to push out concentric tube telescope booms to extend the sun shield. There are 5 layers to this sun shield, and it's critical that there be separation in these layers so that heat from one layer can escape out before it hits the next. So they'll tension up the system, which is just a pulley system that raises the layers apart and provides tension to them. The next deployment is a flap in the back that you can think of as a sail, because it's there to balance the solar photon pressure that would tip the telescope over if that were not there to balance. The center of pressure and the center of mass aren't exactly the same.
That's ridiculously cool.
That's the cryo cooler starting for that mid-infrared instrument, a little refrigerator to keep it super cold. And here, after about 10 days or so, the secondary mirror comes out, and it's at this point when light can actually, focused light can get into the science instruments. There are a lot of radiators that get deployed during this sequence. And then we bring drop leaf table style, the two wings come out. So after about 2 weeks, the major, I call them visible deployments, are done. But then the mirrors themselves are held down to that backplane structure for launch. They get released, and we begin to start moving those as they're cooling down and begin to bring them into shape. It takes about a month for us to get out to L2. We're cooling down this whole time, starting to commission the instruments. We're a little bit like a planetary mission in that we'll launch, fire and smoke, a lot of activity. The first data don't come out until 6 months after that. So after the launch, if you don't hear anything for 6 months, it's okay. Well, that's a big activity we have now, is how do we bring along the public, the taxpayer, with all the activities that are going on, even though we're not seeing data yet.
Well, those first 2 weeks, will we be able to follow along live with each and every deployment?
Yes, that's going to be a big part of, again, bringing people along for the ride. Is we have social media accounts describing, this is what's going to happen today, and here's how we know that happens. We don't have any pictures. And there's nothing that will be taking a picture of us while we're out there, but we'll have great computer simulations showing the state of the spacecraft. So once we get out there, what in fact will Webb do? So we know already that it will be looking for these first galaxies, and here you see an enormous simulation of the universe with dark matter in the purple, where visible matter is accreting at the dark matter centers and galaxies are beginning to form. This is the reason we built Webb. We know this is the science it's going to be able to return for us. So that's certainly exciting. The other thing that has become, I think, maybe even more exciting for a lot of people is this notion of exoplanets. As I mentioned, when we first conceived Webb, we didn't think we were going to be doing exoplanets because we only knew of 2. Well, now we know of thousands. And the way Webb will really contribute is in the cases where you have a transiting exoplanet, an exoplanet that goes between us and the star, and we will look to see if that planet has an atmosphere that subtracts certain elements of starlight from it. So we are really going to be looking for habitable atmospheres with Webb. It's got the mirror size needed to do this. It will still be challenging for Webb, but it will be the first telescope that you'll really be able to go after this in a very big way. And so this is something that we already know is going to be a big focus for Webb, even though when we built it, it wasn't conceived that we would be doing that. The infrared capabilities of Webb will allow us to peer inside the birthplaces of stars and planets within our own galaxy. And we already have seen there are programs, I'll talk a bit about more of those in a second, where people are going to be doing just this. So another way to watch star birth in our own galaxy. Even though it's a big telescope designed to look at the distant universe, it will be able to do amazing things within our own solar system. Now, because of the configuration, we can't look at the inner solar system. So we can't look at Venus, we can't look at Mercury, can't look at the Earth. We can look at Mars. You can do weather, global weather on Mars by looking at it with Webb. I really think most of the time will be spent on looking at the large moons in the outer solar system and the trans-Neptunian or Kuiper belt objects. Again, with the infrared capabilities, it's a great thing to study those. A lot of words up here. The main thing is the link at the bottom. We already know some of the first things Webb is going to look at, and these are the so-called early release science programs. These were competitively selected, and they range from distant universe observations to looking at bodies within our own solar system here. So already the community knows what they want to do for the first things that Webb is going to look at. And if you want to follow along, like every person and or spacecraft these days, it has a Facebook page and a Twitter account. And
Is it going to talk in the first person like, oh, I stretched my wings
actually,
today?
a bunch of us don't want it to do
I
that.
know, exactly. I was like, oh, please.
Yeah. So, yeah.
It sure is cold out here.
Yeah. I can already see the bad jokes. They won't be from me, I'll tell you that. The top link there is the main one, and NASA has a lot of, you can get to a lot of hardware images and movies and whatnot, and the one below it, the webtelescope.org, is the one that the Space Telescope Science Institute runs, and that's going to be focused more on the science that comes out. So that's a little bit, it doesn't have as much on it right now because we haven't done any observations yet. But I'm looking forward to the launch in March of 2021. 6 months after that, the amazing science will start coming out, and so, keep on the lookout for those, and I would be happy to take any questions you have about Webb now.
So we have a little time, 1, 2, 3, and then I'm going to look to that half of the room, which doesn't have any hands up, so get your hands up in a second. We're going to take these 3.
Does Webb have a gyroscope to stabilize it? And is there going to be a possibility of, if everything doesn't work right, to have a servicing, 1.5 million miles is a long way, but a manned servicing mission?
Okay, so I'll repeat the question back. Does it have gyroscopes? How does it stabilize? And the one that a lot of folks ask, is Webb serviceable? So it does have gyroscopes and reaction wheels. We use the reaction wheels to point the telescope. By using the conservation of angular momentum, we have 6 wheels. You'd need 3 of them at a time. They're all at slightly different angles, and by spinning them at different rates and changing that spin rate, you can move your telescope. So that's how we'll move about the sky. And then eventually those wheels can become what's called saturated. They spin up too fast, and you need to de-spin them, and you do that by pushing against rocket thrust. So we have thrusters that we would push against the reaction wheel, and that gives us our life-limiting feature, which is fuel to desaturate the wheels. We're going to carry up enough fuel for about 10 years of operations. If we get a good injection, meaning we don't have to burn any to correct our orbit, we'll get more. And I suspect as people at the Institute learn how to construct an observing program that builds up this momentum in a very small way, we may even get more time. Second question about servicing. Because we're going 1.5 million miles away, we have no way of sending people there today or even in the Webb lifetime. So serviceability was not something we built in to the design. In fact, our instruments are distributed in the sense that you can't just go in and take that NIRCam out because the electronics are in a different place. What we have done is placed optical targets on the bottom of the spacecraft in the ring that attaches to the rocket. And so in the future, if there's some advanced robotic thing that could go up there and latch onto that, it could possibly refuel. That's about the only thing you could do for Webb. If there's a flaw, it's so distributed you couldn't repair. one of the reasons Webb is so expensive is that we've had to have a very elaborate, detailed, lengthy test program to make sure we have redundancy and multiple ways to do things so there are no failures on orbit.
Yes.
The micro shutters.
Yes.
The I assume those are for occultation.
It's
keep the image focused on one thing. So you can,
right. We'll use those primarily when we want to take spectra of lots of galaxies in a field, but we don't want spectra of stars that happen to be in the field or interesting or uninteresting nearby galaxies. So we'll keep those parts of the sky blocked out, and we'll just let light in from the things we want to see. Another place where we might use those is in, say, like a cluster of stars where there's a few hundred stars in that cluster. We only want the spectra from those and not the background stars. So we just let the light in from the objects we're interested in.
does that whole thing move in and out of the way, or is it always there?
You can move it into the field of view. That same instrument has a more traditional, just a long slit spectrograph, a single slit, and it has an integral field unit. So you could move your small objects into those fields. Otherwise, you just open or close the shutters you need.
Okay, and did you not have a question? You were the third? I thought someone over here was third.
Yeah.
Okay.
First of all, thank you for a great talk. And I have a why don't you?
Okay.
Why don't you offer a ride to some university to build a CubeSat for the purpose of observing the telescope as it deploys and does all that stuff?
So one of the things I did over the past year was look at that very possibility, and it's actually dangerous. So the way, if you wanted to observe the telescope, the way to do it would have been to build cameras right into the thing itself. Most spacecraft don't do that. So now, after the fact, we looked at, could you take things on the Ariane 5 with you to go? First off, Ariane would say no, we're spec'd out for this. And you then have you'd have to worry about control of your CubeSat, a few $100,000, $10 billion observatory. Don't want any of that. So in the end, we even looked at, well, what about a large telescope? What if you built, say, for the lunar program, another Hubble, and you sent that a day or so later, and then afterwards, it went back to the moon, it did something there. Then you ran into the problem of the launch window constraints get so tight. If somebody has a problem, then you miss it and now you can't catch it. So you'd have to get a CubeSat. The other thing would have to get pretty close, because the telescopes on a CubeSat are going to be only this big, and so to make it an interesting image, you'd have to get close enough that people worry about collisions.
Anyone on this side of the room? Yes.
Hi, I don't know much about telescopes or space technology, but do you know if machine learning was used for any major or minor design choices in Webb?
To my knowledge, machine learning was not used in any of the design aspects. Much of this design work was done in the early 2000s, before a lot of the machine learning was, I think, applied in many industries. I think what we're trying to do now is use it more in designing observing programs and mining data for Webb, and that's where I expect it will make a big difference there.
Cool, thank you.
So I have a question, and then lastly, but I'll go before you, because what do you want to observe yourself? And are they giving you time just because of all the years you've put in? I guess that's part two.
So one of the things when you work for NASA, and particularly at NASA headquarters, you're there to create science programs for the science community. So we don't get any time at NASA. And I think that's actually good, because we can actually do things very objectively. If my goal was to observe object X, it might influence my decisions as to how to fund
To
things or
optimize that instrument
optimize it
for-
for
yeah.
that. So we do things for the best of the science community. If I were going to pick something to look at, I would probably, one of the galaxies in my thesis was NGC 1275, radio galaxy, active galaxy. I would probably look at that to see about how the star formation in the inner region relates to any of the activity at the center, or is it a remnant of the collision that spawned the system? But,
Thank you.
But I'd have to write a proposal if I
Yeah.
want to do that. Yeah.
And our last, okay, 2 questions. You, and then I'm done.
My question was, what were you most excited to learn about from Webb, which you just kind of answered.
Well, that would have been if I was doing my old science again. I think the most interesting thing that I know it's going to do is probably some of these exoplanets looking for habitability, the TRAPPIST system. But as I was saying a little earlier, usually the best or the most fascinating science that comes from these great observatories is something we don't even think about today. So somebody is going to think of some novel use that people will initially say, well, that's a stupid idea, it's not going to work, you can't do it. And eventually it will be an amazing discovery. So that's what I'm looking forward to.
Web deep field.
Okay,
they'll do
and
that,
our
yeah.
last question is at the top. Oh, I saw you too late. Yeah, go ahead.
Is there anything special about L2? Is it any noteworthy? Is it going to be a subject of research for the telescope at all? Is it anything like going on with L2?
So L2 is a special place because it's a semi-stable point, so you don't need a lot of fuel to stay there.
Is it just a point or is it a planetesimal body?
It's just a point in space. There's nothing there. Because it's semi-stable, if you put something there, any perturbations to it, a little pressure, hit by something, it will fall off L2. L4 and L5, those points are stable. And in fact, if you look there, collections of dust exist in those places. But we go to L2 because it's far away from infrared sources for us. It's semi-stable, so we don't need to use a lot of fuel to stay there. And in fact, a lot of science missions have already gone there, and future ones are going to go there. So, but it's a big place, so it won't get crowded.
Okay, I'm going to call an end to the questions, sadly, because I know everybody has a few more, but we have a few things we just want to share before we go to our break. So let's thank Dr. Smith. And we made this poster for the talk tonight before seeing you today, so one of our staff, Jeff here, updated it a little bit there. As we said we would.